Hello everyone, welcome back from the extended spring break, and last time we finished section 14.3 partial derivatives, but thought maybe a quick review would help get us back into things. So recall the notation. There's two different types. We've got the partial derivative with the delta f over delta x, so read as the partial of f with respect to x, and similarly this is read as the partial of f with respect to x as well. And that's where we take the derivative with respect to x and hold y constant. F sub y, or the partial of f with respect to y, is when we take the derivative with respect to y and hold x constant. Then there's second order partials, derivatives with respect to x twice, with respect to y twice, and then our mixed partials with respect to y, then with respect to x, and then this is with respect to x and this is with respect to y. So notice that notationally they're a little bit different, because when we say f sub y x, for example, we're talking about y first, x second, as opposed to when we take the second partial using the differential notation, we're talking about taking y first, and that's listed second in the bottom portion of the notation. So just notice that little difference. So here's a quick example. Basic function, just a nice simple polynomial, and I want to find all six partials here. So let's see. So part A, partial with respect to x. I won't use the functional notation. So derivative of x to the fifth, 5x to the fourth. Derivative of y to the fifth, if y is held as a constant, then its derivative is 0. But when we have a product of x and y is held as a constant, so we're differentiating x to the sixth, so that's 6x to the fifth. So we'd have plus 6x to the fifth, and then the y to the seventh tags along as a constant. Derivative of 8x would be 8, and derivative of 9y, negative 9y that is, would be 0, because again y is a constant. So I'll do part B here, and that's the partial with respect to y. So now x is a constant, so the derivative of x to the fifth is 0. Derivative of negative y to the fifth is negative 5y to the fourth. Here the x is held as a constant, so remember you can cover it up, differentiate y to the seventh, you get 7y to the sixth, then make sure you tag along the x to the sixth as well. And then the derivative of 8x, since x is a constant, that's 0, and the derivative of negative 9y would just be negative 9. Okay, we'll go to part C, is the mixed xy. So that's going to be focusing on the partial with respect to x first, and then with respect to y. So looking at A, we're now differentiating with respect to y. X is held as a constant, so 5x to the fourth goes to 0. For this term, y to the seventh, it differentiates to be 7y to the sixth, times 6y to the fifth would be 6x to the fifth, 42x to the fifth, y to the sixth, and then the derivative of the constant, of course, is 0. Okay, so now for the other mixed partial, f sub yx. Focus on part B, because this means y first, then x. So now we're differentiating with respect to x, so y is a constant, so negative 5y to the fourth goes to 0. The 7x to the sixth, y to the sixth. We're holding y as a constant, derivative of 7x to the sixth, 42x to the fifth, and the y to the sixth tags along as a constant multiple, and the derivative of negative 9, of course, 0. And remember, we did have a theorem when we covered this that the mixed partials as long as the functions are continuous, the mixed partials will be equal. Okay, so that's kind of a little verification. Part to part E, that's x twice. So we'll focus on part A and differentiate that with respect to x. So 20x cubed. Y is going to be a constant, so 30x to the 4th. And the y to the 7th takes along. And then the derivative of the 8 is 0. So that's all for that one. And then for part F, with respect to y twice, focus on part B, differentiate that with respect to y, we get 20y cubed, negative, and then here the x is being held as a constant, derivative of y to the 6th, 6y to the 5th, times the 7 would be 42, the x to the 6th tags along as a constant, and that was y to the 5th. So those are the partial derivatives for that function. Here's a function a little bit more interesting. That's e to the, trying to focus here. E to the x cubed, y to the 4th. And so do the same 6 partials. But now get used to the different notations. So we have to be versatile, of course. So partial of f with respect to x. Okay, so that's the formula for e to the u, which is e to the u. So e to the x cubed y to the 4th. But then times the derivative of that power on the base of e. And the derivative of x cubed y to the 4th with respect to x holding y as a constant would be 3x squared y to the 4th. So maybe rewrite this as 3x squared y to the 4th e to the x cubed y to the 4th. Okay, and then for part B, that's the partial with respect to y. Going to be similar, e to the u again, so e to the x cubed y to the 4th, then times the derivative of the power, but now we're differentiating with respect to y, so x is a constant, so that would be 4y cubed, so let's write 4x cubed y cubed. And rewriting this, 4x cubed y cubed e to the x cubed y to the 4th. Okay, now for the mixed partials. So part C, partial, second partial of f with respect to y now after taking it with respect to x. So we're going to be focusing on part A. And now we're actually going to need the product rule because we have, we're doing this with respect to y, and we have a function of y times a function of y. So by the product rule, first factor, 3x squared y to the 4th, derivative of the second, derivative of e to the x cubed y to the 4th again, recopy. Now we're differentiating with respect to y. So that would be times 4y cubed times the x cubed, 4x cubed y cubed. But then plus the second factor, e to the x cubed y to the 4th times the derivative of the first and the derivative of 3x squared y to the 4th. Okay, we're differentiating with respect to y again. So that would be 4y cubed times 3x squared, 12x squared y cubed. So maybe multiply the 4x cubed y cubed by the 3x squared y to the 4th, and we get 12x to the 5th y to the 7th, and then our e to the x cubed, y to the 4th, and then plus, bring the 12 x squared y cubed out in front of the e to the x cubed, y to the 4th. Okay, I think we'll just do part D here, and then we'll skip these ones for now, because they're going to be very similar, but at least let us show that the mixed partials are in fact equal. So now the second partial of f with respect to x after taking it with respect to y. So now we're going to focus on part B solution, and so we're going to need the product rule again for the same reason. So function of x times a function of x. So first factor 4x cubed y cubed, derivative of the second, derivative of e to the x cubed y to the 4th, formula for e to the u again, so e to the x cubed y to the 4th, but then times the derivative of the power with respect to x now would be 3x squared, and the y to the 4th tags along, and then we have plus the did I do that right? Yeah, then plus the second factor e to the x cubed y to the 4th times the derivative of the first, and the derivative of the first is the derivative of 4x cubed y cubed, which would be 12x squared y cubed. And so that gives us 12. Here we've got x cubed times x squared, x to the 5th, y cubed, y to the 4th, y to the 7th, and then our e's, and then plus, let's bring this 12x squared y cubed out in front of the e to the x cubed y to the 4th. Okay, so you can see that, again, those mixed partials are equal. So I'm not going to bother to do parts D and E. I guess I get a little bit ambitious when I wrote up these notes. You can do them for fun if you like, but actually they were even supposed to be, this was supposed to be with respect to x twice, and then with respect to y twice. But either of those would require, just as parts C and D did, the product rule, so be kind of redundant, and so we'll just leave it at that. Okay, I'm going to try to cut these videos rather short because the downloading time, if I go too long, the downloading time makes it a little bit cumbersome. So I'm going to stop right there, and we'll come back and we'll start. So that was a quick review for section 14.3. And then we'll come back and we'll start with section 14.4.